G'day, I'm Dr. Kev, and this is an Enkei RPF1 15 by 7 inch wheel. And in this video, I run through how I took a scan of this wheel, created a SolidWorks CAD model, and at the end of the video, I put it into the suspension model for Project 171. Welcome to Car Design Workshop. Laser scanning is a pretty cool way to measure parts and assemblies. And in this video, I'm going to be using a Creon scanning arm with a blue light laser to scan the Enkei wheel. Well, I've done a bit of scanning in the past, but I'm not really an expert at it. I only do it occasionally. So this video is really going to show the methods that I would use to try and get to a model as quickly as possible. These scanning arms can measure complex geometries with a high level of accuracy. They project a laser beam onto a surface, and a camera captures the reflection of that beam. And in a lot of ways, working with these arms is very similar to working with the light and camera that you would do during video. At the beginning of the process, you really want to have a good idea of what you're trying to get from the scan. Are you looking to have a reference scan where you're able to catch some of the key dimensions, but you don't need every last detail scanned? Or are you after a really accurate graphic representation? Or do you want to go all the way to a watertight model suitable for a solid model or even 3D printing? Now, each of these levels is possible using a scanner, but they're going to require differing levels of time in the original scan and certainly different levels of post-processing. A scanning arm can collect a lot of information about the geometry very quickly, which means when you're doing that processing, a lot of computational power might be required. Now for this scan, I knew I was going to create a solid model in SolidWorks afterwards. So I wanted a file with not too many points, and a reference model was going to be fine. I didn't want to have to do a lot of the post-processing. You can end up losing a lot of time in post-processing for not a huge amount of benefit for the final SolidWorks model. Now, one advantage with this, in this case, I knew some of the key dimensions, such as the wheel offset, the wheel bolt PCD, and the model was going to be mainly used for clearance to parts in the wheel and to look representative of the final wheel. I don't need to create a model good enough to manufacture the wheels because these are a purchased item. I like to think of the scanning process as a little bit like a mix of spray painting and taking a video. And what I mean by spray painting is that you're effectively moving a line created by the laser over the entire surface of the object as if you were covering it with paint. And the video that you're getting from the scan is really covering what that line exposes on the final part. So we need to think about the light that's coming back to that camera. Now you can set the exposure of that camera manually, but the software these days is pretty good at the auto exposure and you generally get pretty good scans. There are a lot of other settings that we can play with, really about noise and distances between scan lines. But whenever possible, you try to keep these relatively consistent between projects. Now, I've managed to get settings wrong far more often than I've got them right. So when we find settings that work reasonably well, we try and stick with them. The surface finish of these wheels is a satin black. But when trying to scan it originally, it came out horribly. There was basically no information getting captured at all. So I knew that I had to do some sort of surface prep to the wheel. Now, one solution, and a really good one when you want to capture really good scans, is to spray it with a flat white paint. Now, in this case, I didn't want to damage the wheel. Now, I had heard that a hairspray could work as well, but I didn't want to risk anything that was going to sort of mar the surface or stay around afterwards. Now, to avoid damaging the finish, in this case, I used baby powder. Now, this is very difficult to evenly apply. I did use the bottle to sort of squeeze it on as a cloud, and then a brush just on a couple of the areas where I might have handled it and removed the baby powder and it had gone shiny again and wasn't picking up on the scan. Now, it wasn't a uniform coverage, and a little bit of time spent here could have maybe improved this process. I could have also used something like targets. You can get small sticker targets that you could put on the different surfaces that help align the scan, but in this case it wasn't needed. Now, in the process of the actual scan, there is a green dot that the scanner projects onto the surface, and you try and align that with the blue laser line, and that helps you to regulate the distance. And I'm trying as much as possible to keep the laser normal to the surface, so 90° to the surface as much as possible. If the laser can't reach the area or the camera can't see the area, it can't be scanned. And this means that holes are very difficult to capture well in a scan. And if you do want to get these holes more accurately, that's when you can attach a probe to this scanner and manually probe some of those features. Now, in the process of scanning, you really do multiple passes, just like you were doing spray paint on a surface. And the software is going to overlay those different scans. And what that means is that a lot of areas of the surface are going to be covered multiple times. And so you can generate a large number of points, and you want to make sure that you reduce some of those points. And the software is pretty good for this. And one of the ways to remove a lot of the points is just to resample it, where you make sure that the points are evenly spaced. And for this, I didn't need a huge number of points, so I ended up with a reasonably rough model, but it was fine for the next state. To do the scan of the wheel, I had to do a scan from the outside of the wheel, capturing all of the outside features, and then flip the wheel over and do a scan from the inside. Once you have both the outside and the inside scans, you need to align them to make a scan that's going to include all of that detail. Now, the way we do this in the software is to pick 3 or more points, and the more points that you have, the better, that exist on both of the scans. So you need to make sure when you're doing the scans that there are areas of the wheel that you're covering in both directions of the scan. And that does a rough alignment of the two main scans, and then the software can do a best fit of that. Now, if you have a lot of points, that best fit can take a very large amount of time. If you've already done some reduction of the number of points that you have, that can be a much quicker process. Now, one thing I should note is that when you are doing the scan, you often scan some sections that are around the wheel. So I might grab some of the table accidentally and scan those. And before aligning the scans, I basically delete some of those sections, so that it makes sure that the only points that are included in the scan are those that are on the wheel themselves. Now, because I knew that I was going to take this scan into CAD and really just use it as a reference, I wasn't too worried about getting absolutely every part of the wheel completely covered. I did make sure that I had a few of the spokes very well scanned from multiple directions and try to avoid gaps on all of the spokes so that I would have that information when I went to model it. And I did spend a fair bit of time trying to get the area around the wheel bolts, because those holes are quite hard to capture, and I wanted to make sure I gave myself the best chance to have that information in the scan when I went to model it. Now, there's some really good software that you can use to extract different geometries from the scan, software like Geometries or Polyworks. I really just wanted to take this as a graphics model into SolidWorks and just work from slices of the model. I did need to align the model, so I created a plane on the back surface of the mounting face, and I grabbed the center of the wheel and one of the wheel bolts. And that just helped me to align the graphics to planes that I would then be able to use when I went to SolidWorks. And once all of the data was aligned, I just exported that to an STL file, which I could open up as a graphics body in SolidWorks. So when it comes to using this model in SolidWorks, CAD, I wanted to use this in what's going to be a full car model. And that car model is going to have hundreds, if not thousands, of parts. So I want to make sure that all of my models are fairly simple. If I end up having a lot of scan details, I'm going to end up with a lot of big files that are going to really slow down the full car assembly. So I want to make sure that when I do the modeling, I'm using as few features as I can, and I'm capturing the design intent as concisely as possible. Now I know taking this scan in that the dimensions won't be exact. There's errors in the scan, and there's going to be errors in converting that scan to a model. But as long as I'm within a millimeter or so with most of those dimensions, it's going to be well within the clearances that I intend in the final design. Now, I'm also aiming for this model to be close to mass accurate. I would accept a reasonable amount of error, but I want to make sure that the model is properly representative of the part that I have scanned. Now, the main feature of the model is really one big revolution. And to get the dimensions for this, I would slice through the graphics body on a slicing plane and pretty much try to copy the profile with a combination of arcs and lines. I did use splines for the spokes to try and make sure that they were as close to what was in the part as possible. So a fair amount of time was put into that main revolution. Nearly all of the details of the model are captured in that first revolution. This is a lot of just going line by line, arc by arc, until the sketch that you have for that revolution matches pretty closely with the scan that has been there, knowing that some of the key dimensions, such as the offset, you have from the specs of the wheel. Now, typically, if I'm trying to follow the profile of the scan, I will sort of round over to the nearest 1/2 mil most of the time. And I know that does bring in a slight inaccuracy there. So the model that I'm dealing with at best is going to be within a 1/2 mil of the dimensions of the scan or of the original wheel. Once the main revolution is modeled, I then have two different shapes in this particular design from Enkei that will conform the cutouts to make the spokes. Now, these spokes were quite hard to get accurate, and I would say these are the least accurate parts of the model. And part of that reason is that the spokes actually have a taper to them. Now, to keep the model fairly simple, I just wanted to have a simple shape that had a constant taper on the cutout. Now, I don't think that's exactly the geometry of the Enkei, but I think you'll see at the end, it matches up pretty well. So once we have those first two holes cut out, it's a simple case of just doing a pattern of those, and those holes are repeated 6 times around the circumference of the wheel. Once we get to this point, the wheel is already looking very, very close to the final item. The next step that I did was to cut out a wheel bolt, and I did this as a revolved cut so that I could put details around the taper for the wheel bolt. And once we have one wheel bolt, it's a simple step to then do a pattern of those wheel bolts to end up with all 4. Now, the last main feature was to do a patterned or rear pattern weight removal, and this is on the mating face of the wheel where some of the material has been removed. Now, the detail around this was reasonably complex. I just wanted to do, again, a very simple tapered cut through here. So I simplified the geometry a little bit, and it's not a really big loss. None of this geometry is visible at all in the model. This is going to be mated up against a hub, but it is good to have this weight removal because it's going to make sure that the wheel's mass is much closer representation of the actual wheel. Now, when modeling just about any part in a CAD package, I like to put the fillets at the last main feature, and that means it becomes easy to turn these fillets on or off. Fillets also have a way of disturbing the underlying geometry, so if you're wanting to go and make this a fairly modular model where it's easy to go back in and change dimensions, if the fillets are done too early, that often mucks around with faces that you might select for other procedures. So I think it's just good practice to have them there at the end of the model. If we take a centerline slice of this model, we see that the details of the wheel are really captured quite well. We see the beads that hold the tire on, When loaded, we see the material that is thicker where the spoke joins to the rim, and we see the outward arc of the spokes to clear the brakes. And you can see a lot of the really good design intent once this is modeled. And I've got to say, I'm quite happy with the design of these wheels. I think it's a really good product and it should work really well in the vehicle. Now, this model was achieved with 9 main features. So the revolution, the spoke cutouts, the wheel bolts, the mating face, weight removal, those fillets, and then a final feature that allows for the addition of a tire valve. So a fair amount of complexity captured in really just a few features. And if we see this overlaid with the original scan, you'll see that there's quite a lot of good correlation here. We see that in some places there's a little bit more material in the scan, and in some places there's a bit more material in the model. But overall, you see the geometries match quite well. And we can see this quite clearly if we take a photo of the rear wheel and put it up against the model of the wheel. You'll see that they match up quite well. I will also note that when adding an appearance to the part, I'll often choose something with a little less gloss to it. That makes it a lot easier to work with in the overall car assembly. It's less visually distracting if you have less reflections of these items. I'll also generally model black parts as being a dark gray rather than a really black, and that means that you can see some of the features a little bit easier on a computer screen. And the last thing when it comes to modeling is that once we have this modeled, we can apply the material as being aluminium, and then we can calculate the mass properties, or have the software calculate the mass properties for us. And this comes out weighing at 4.62 kilograms. Now we also get moments of inertia of the wheel, which can be really helpful once we start to do vehicle dynamics calculations. So now we move on to the final part of this video. And first up, let's just weigh the original wheels. And as we see here, the real wheels weigh 4.45 kilos. Now with the model coming out at 4.62 kilos, that's an error of about 4%. And I'm pretty happy with that. Now, most likely these errors are due to some of the errors in measuring, some of the errors in giving only around a 0.5 mil accuracy on some of the line locations and radiuses, but also I haven't accounted for any thickness to the finish applied to the wheel. So when we are doing the measurement and the scan of the wheel, we're actually scanning the outside dimensions of the finish, and that finish will have some thickness. Whereas in the model, I've assumed that that model is all just one density, and that's the density of aluminium, which is denser than whatever coating might be applied. So there will be some overestimate of the model weight. Now with the mass properties, we can override the mass and we can override that density, but I intend to keep it as it is. It's generally easier to underestimate the weight of components, and having a little bit of extra mass in this model is going to help to account for any weight where we're adding with, say, balance weights or the tire valve. So an obvious question is, now that we've gone through the process of scanning these wheels and modeling them, is it a really good solution for Project 171? I had initially modeled the car using a Raise Volk TE37. These are a really good forged wheel, and each wheel comes in at 4.3 kilos, and the total cost for 4 wheels was going to be $3,300. Now these Enkei RPF1s, they're 4.45 kilos a wheel. And so that's a total of 600 grams extra for the whole car. And so we can see the weight is pretty similar between these Enkeis and the Raise wheels, but the big difference is in the price, with the Enkeis coming in at 4 wheels at about $1,500 Australian. Now I'm not sure what I'm prepared to pay to save 600 grams, but it probably isn't nearly $2,000. There's better places that I could put that money to save weight elsewhere. And when it comes to aesthetics, I think the Rays are a fantastic looking wheel, but they're not a wheel that really evokes that 1950s look. I think the Enkei, it's not really an old style, but at least the thin spoke look is probably more reminiscent of the wire wheels and the thinner wheels that we would have seen in the 50s. So we can see this Enkei wheel now in the updated corner model, and there's a few things that jump out straight away. The brakes, as they're modeled, are now very close to the rim. And now I will address this when spending a bit of time designing the brake system, and I'd already decided to make a few changes in that way and really just reduce the overall size of the disc and change the attachment method of the brake caliper. So I'm not overly worried about that at this stage. But the offset is different than the raised wheel. So the raised Volk had I think a 45mm offset. These are a 35mm offset. So we'll have to have a look at the geometry, but none of the steering geometry had been finalized. It was purely a placeholder geometry, and we should deal with that in a later video. Otherwise, I think the wheel works quite well. Now, this process of scanning and modeling, this is a process that's likely to be repeated with a lot of parts. For many of the simple parts, we don't bother doing the scan. We can just get a good enough model with hand measurements. And in fact, even with the wheel, you can get pretty close just taking hand measurements off and really save you the time of a lot of this process. But wherever there is a little bit of complexity in the objects, going through this scanning process can really help you get a more accurate model and help with the clearances in your final design. Well, I hope you've enjoyed this video, and I thank you for your time.